Suppose now I'm analyzing an algorithm. I've determined t of n, and I found maybe my t of n equals, oh, let's just call it 1/2 n times n plus 1. Right. So you remember this, we talked about this last time. This is the number of dots in a triangle, right? This is also the number of executions of certain kinds of doubly nested or of singly nested for loops. So suppose t of n is this, and I'm trying to determine what's big theta, what like t of n is big theta of what. So I could ask a question like this, for example. I could say, is t of n big theta of n? Question mark. Or is it big theta of n squared? Question mark. Right. So suppose I'm trying to determine whether some running time, some t of n expression that I have is big theta of n or big theta of n squared. How might I do that? And what's a really simple way that I might think about doing this? And maybe even from an empirical standpoint, how might I think about doing this? Well, here's one way you can approach this. So last time, one of the things we did is we said, well, let's think about t of 2n divided by t of n, and we could plot this. And part of the reason I was thinking about this is that thinking about orders of growth in terms of ratios can be really helpful, right? So if this is big theta of n, then I should have 2. If it's big theta of n squared, I should have 4. So this is one way you could do it. You could try to actually plot this kind of expression and see kind of what order of growth you get, like see if it levels off somewhere. Another approach would be to plot these against each other. So suppose I've got this t of n. Let me actually plot it on the same axis as n squared. Right? So let's think about what t of n would look like if I plotted it near n squared. So here's my t of n. T of n. And here's my n squared. And I could eyeball this, and I could say, hey, look, those two look pretty similar, right? Those are tracking each other well, but are they tracking each other perfectly, right? And I would ask, are they tracking each other perfectly? So what would I do if I wanted to figure out if they're tracking each other perfectly? I might plot more points, right? I might just zoom out and plot more points. So what am I going to do? I'm going to say, let's just zoom out. Okay. Now suppose I zoom out and I see the following, right? Suppose I zoom out and I get this. So suppose this is what I see, where this is t of n and this is n squared, right? What would that mean? Well, it would mean that these two look exactly the same as each other once we've zoomed way out. Okay? And so let me propose a different ratio to you than the one we were looking at before, and talk about what that ratio would be in this case, and then talk about if that ratio comes to something else, what does that tell us? So here's a ratio that it's going to be kind of universally helpful for us. So let's think about the ratio t of n divided by n squared. Now let's think about taking this ratio in a limiting sense. So let's say, what is the limit as n approaches infinity of t of n over n squared? And I want to ask, and you may pause the video and think about this, if this plot is what I get when I plot t of n and n squared and then zoom way out and plot out to 20 billion or something like that, what would this ratio evaluate to? Well, this ratio would simply evaluate to 1. Right? So if this ratio evaluates to 1, what does that mean? It means that t of n essentially equals n squared when n gets really, really large. This means t of n, and I'll write wiggly equals because it doesn't have to equal for small n, but t of n basically equals n squared when n is large. Okay. So this is nice, right? So it's a handy thing to have. Like if I were to evaluate this ratio and the ratio evaluates to 1, I could say, look, these two are basically the same as each other, which is strong evidence, right? That this is that t of n is actually big theta of n squared. Okay. So what if I got something else? What if I didn't get 1? What if I got something like a half. Okay, so first let's just think about what the plot would look like if I evaluated this ratio and it came out to a half. The plot would look something like this. So here's my question. What if the limit as n approaches infinity of t of n over n squared equals a half, right? What plot would be consistent with this? Well, it'd be a plot that looks like this. Here's my n squared, and here's my t of n. Right? It'd be a plot where t of n essentially settles down to about half of n squared, right? So, you know, this if this is 1, then this is a half. Right? If I get rid of the units and just look at the ratios, that's what this would look like. All right, what does that tell me? Well, that tells me that t of n is big theta of n squared. And why is that? Because t of n never gets very far away from a constant multiple of n squared. Okay. So this means that t of n is big theta of n squared. Okay. So now this is nice, right? So it's a handy trick. Let's think about what would happen if this ratio evaluated to something completely different, right? So let's think about what would happen, for example, if t of n were not big theta of n squared. Right, so here's a question. What does the plot look like if t of n is not big theta of n squared? Okay. Well, how would that show up? Well, let's draw a plot, right? So let's draw a plot and then think about what it would mean, right? So what if I got something like this? So what if I got a plot that looked like this, where I have, you know, initially n squared goes up like this, and then, you know, t of n looks like this. And then when I zoom out, here's my zoom, my plot looked instead like this, where now n squared still shows up, but t of n just gets smaller and smaller and smaller. So t of n is way, way, way down here. T of n is way, way, way down here. So in a situation like this, if I zoom out, and I can still see n squared, but t of n kind of squishes down and squishes down and squishes down. What this means is that t of n just can't keep up with n squared. And so if I were to evaluate the limit as n goes to infinity of t of n divided by n squared, what would I get? The limit would be 0, right? What this is saying is that n squared is totally running away from t of n. And so as I evaluate this limit, I end up with 0. Right? And so what would this tell me? Well, think about the plot. Right? What is this plot saying? It's saying that t of n is sort of arbitrarily smaller than n squared. And I can make that gap as big as I want by making n really, really large. So this means that t of n is asymptotically upper bounded by n squared. Right? So if I end up with a situation where n squared is just running away from t of n, that corresponds to this limit being the case, where this limit, the limit of this ratio is 0, and that corresponds to t of n being big O of n squared. T of n being big O of n squared. Right? Remember that the big O means less than or equal to, right? So I'll put in quotes, this is like less than or equal to, and less than or equal to actually includes strictly less than, right? So if we have a situation like this, then what we can for sure say is that t of n is big O of n squared, and t of n is not big theta of n squared, right? So if this limit evaluates to 0, that had better mean that t of n is not big theta of n squared, right? Because it can't keep up, right? If it were big theta of n squared, it would be able to keep up and at least still show up on the same set of axes. But if t of n just squishes down to 0, then it's clearly not big theta of n squared. All right, so we can do one more case. So we can say, okay, what if we have a plot and, you know, at first we have n squared. Oops, let me write that in red. So here's t of n, and here's n squared, and it looks like they're tracking. But then we zoom out, and n squared squishes all the way down to nothing. So what if we were to zoom out, and we could still see t of n, but n squared is squishing way down here to nothing, right? What does that mean? And so, oh, by the way, this arrow here, this is supposed to indicate that we're plotting many, many more points and zooming out, right? All right, so what does this mean? Or at least what version of the limit would this correspond to? Well, this would say t of n is running away from n squared, right? So t of n can become unboundedly larger than n squared. And so the limit would look something like this. The limit as n gets very large of t of n over n squared would evaluate to infinity, right? What does this mean? It means that t of n gets unboundedly larger than n squared. And so what's the situation here? Well, clearly n squared is a lower bound, an asymptotic lower bound for t of n. And so this is to say that t of n is big omega of n squared. And t of n is not big theta of n squared, right? T of n is greater than n squared, but it is not equal to n squared in an asymptotic sense. Not big theta of n squared, right? So there's the basic layout of how the limit test works. And so we'll formalize the limit test now in the next video.